Hello everyone, in this video we're going to be looking at section 11.2, which is space coordinates and vectors in space. So subsection 1 here is coordinates in space. Notice how I don't say in the plane. Why? Because so far we have been primarily concerned with two-dimensional coordinate system, in other words the coordinate plane. Much of the remaining part of our study of calculus will involve the three-dimensional coordinate system. Right, so finishing up this course, and then if you move on to Calc 3, we'll be doing a lot of work in the three-dimensional coordinate system. Okay, so let's go a little bit into its construction. We can construct the three-dimensional coordinate system by passing a z-axis perpendicular to both the x and y axis and the origin as shown in the diagram. Right, so our x-axis, typically the way most books do it, comes almost like out from the book. And then the y-axis is, again, what we're familiar with, and it goes this way. And so this back here is the negative y-axis, right? And then this back here is the negative x-axis. So this flat space that's in between them, that looks like it was colored in blue in the book, but now I'm coloring over it red, that is the xy coordinate plane that we're used to. So then what we do here is we decide to take the positive z-axis to be perpendicular from that xy plane, right? So in other words, shooting straight up from the xy plane. And again, typically when it's drawn in the book, it's drawn straight up like that. So that's the z-axis. And again, the dotted represents in the negative direction. Okay, so taken as pairs, the axes form three coordinate planes, right? The xy plane, which is the one that I highlighted before there, this would be like the xy plane. And now if we look at the xz plane, the xz plane is, again, the plane that's made by the x and z axis. So it's this vertical one here that slices down. And then the yz plane, again, the one made with the y and z axes. So this is this vertical one that slices down. So these three coordinate planes separate the three space into 8 octants. So remember, in the two-dimensional coordinate system in the plane, we had the 4 quadrants. Now we have the 8 octants, right? So it's this guy up here, this guy back here, this guy back there, this guy up here, and then all the same guys down below to the negative z values. In this three-dimensional system, a point P in space is determined by an ordered triple. Right, so it has an x coordinate, a y coordinate, and a z coordinate. X is the distance from the yz plane to P, y is the directed distance from the xz plane to P, and z is the directed distance from the xy plane to P. So let's look at a couple of examples here of plotting some points in the 3 space. So if we look at point 1, which is 2, negative 5, 3, what does that mean? That means 2 in the positive x direction. Right, so in other words, I go, remember the positive x direction is this guy. So I go 2 in the positive x direction, and then I go negative 5. So I go 5 in the negative y direction. So I go 5 this way. And then I go up 3 because I go positive 3 in the z direction. Right, and I arrive at this point up here in the space. That is the point 2, negative 5, 3. Right? And all the other points are done the exact same way. So maybe we'll look at one more here. So 3, 3, negative 2. So again, how we do this, we go positive 3 in the x direction, positive 3 in the y direction, and negative 2 in the z direction. Right? And that's how we arrive at this point over here. Okay. So many formulas in the two-dimensional coordinate system can be extended into 3 dimensions in the perfectly natural way, and oftentimes in exactly the same way. So for example, the distance formula between 2 points x1, y1, z1 and x2, y2, z2 in the 3 space is given by this formula here. Notice that it's exactly identical to the distance formula in the 2 space, except you just add the z coordinate that you're subtracting the z2 minus z1 and then squaring it. So for example, if I wanted to find the distance between the points 2, negative 1, 3 and 1, 0, negative 2, what would I do? Well, I would just say, okay, x2 minus x1, so I get 1 minus 2 squared plus 0 minus negative 1, so plus 1 squared, plus negative 2 minus 3 squared. right? And if I multiply that out, I end up getting radical 27, which I can simplify, right? That's 9 times 3 is 27. So when I take the square root of 9, that's 3. So this becomes 3 radical 3. So that's the distance between those 2 points in the 3 space. So think about the equation of a circle in the 2 space. Remember, a circle centered at hk would be x minus h squared plus y minus k squared equals to r squared. Well, what's the 3-dimensional version of a circle? That would be a sphere, right? And so if we have a sphere, this time centered at x0, x sub 0, y sub 0, z sub 0, and radius r, it looks the exact same, where I have the x minus the x value of the center squared, y plus y minus the y component of the center squared, and then I just do the z minus the z component of the center squared equals to r squared. And then the midpoint formula, again, we're familiar with the midpoint formula from way back when of in the 2 space, and it looks exactly the same. You just add, again, the z component on there. So looking at this example here, if I wanted to find the standard equation of a sphere that has the points 5, negative 2, 3, and 0, 4, negative 3. Okay, so what I need to do here, I guess I should have put that these 2 points are on the diameter, or these 2 points make the diameter, because that's kind of the assumption we're making. Because first and foremost, if I want to find the center, if those are 2 points that are on, that make up the diameter, right, the 2 ends of, I should put endpoints of the diameter. So the way the question is phrased in the book, I apologize, that has the points, that as endpoints of the diameter. So I should finish out the question. And that's important because now, in order to find the equation of a sphere, we need the center and the radius. So we can find the center by finding the midpoint between these 2 points, right? So we need to find the center. And how we're going to do that, it's going to be the midpoint between the 2 given points. So 5, negative 2, 3, and 0, 4, negative 3. So my center is going to look like x sub 0, y sub 0, z sub 0, and we're just going to take the average of all these points, right? So 5 plus 0 over 2, negative 2 plus 4 over 2, and 3 minus 3 over 2. So I end up getting 5 halves. Negative 2 plus 4 is going to give me positive 2 over 2, which is 1, and then 3 minus 3 is going to give me 0, right? So that's my center. And then what's the other thing I need to write the equation of a sphere is the radius, right? And in order to find the radius, remember the radius is the distance from the center to one of the edges. So I can take the distance from this guy to either one of these points, right? So if I wanted to find the radius, then what would I do? I do that by finding the distance between my center, which we found to be 5 halves, 1, 0, and either of the 2 points. So let's just go with the first point, 5, negative 2, and 3. So my radius is going to be 5 minus 5 halves squared plus negative 2 minus 1 squared plus 3 minus 0 squared, which if I added all that up, or subtracted all that up, squared it, and then added it, I'd end up with the square root of 97 over 4, which is radical 97 over 2. And now the equation of my sphere. So again, what do? We just take x minus the x value of the center squared, and then the same thing for y and z, and then equal to r squared. right? So I would get x minus 5 halves quantity squared plus y minus 1 quantity squared plus, and then z minus 0, so that's just z squared is equal to my radius squared. So if I square my radius, I end up with 97 over 4. So that is the equation of my sphere in the 3 space. Okay, so what have we been talking about lately? Lately we've been talking about vectors, right? Vectors in the 2 space. So now we're going to just extend that to vectors in the 3 space. And again, that's going to extend very naturally the same way everything so far is extended naturally into the 3 space. So in space, vectors are denoted by ordered triples now instead of ordered tuples. So v sub 1, v sub 2, and v sub 3 are our first, second, and third components. And the 0 vector, again, is a boldface 0, and it's just where I have 0 as all 3 components. So the standard unit vectors are somewhat similar, right? The I is where I have 1 in the first component and zeros elsewhere. The J is where I have 1 in the second component and 0 elsewhere. And then now K is the new one here, and it's where I have zeros in the third component, but 1 in the third component, but zeros elsewhere. And so the standard unit vector notation for V is just going to be the first component times I, plus the second component times J, plus the third component times K. Just the same way we did the standard vector notation in the 2 space. Okay, and then this vectors in space, essentially these are just all of the properties that we had in the 2 space, but just restated for in the 3 space. So if I have 2 vectors, the vectors are equal if and only if every single component is equal. Component form, so if I have a point P in the 3 space and a point Q in the 3 space, then how am I going to find the vector that's represented by the directed line segment from P to Q? Well, same thing that I did in the 2 space. I take the first component of the terminal minus the first component of the initial, second component of the terminal minus the second component of the initial, and same thing for the third component, right? So again, it's always terminal minus initial, terminal minus initial. The length is again just exactly the same, right? In the 2 space, we just squared the first and second component, added them up, put them underneath the square root. Now we just add the third component in there. Unit vector in the direction, so once again, just multiplying it by 1 over the magnitude, or 1 over the length. Vector addition, again, it's just component-wise, but now we do it in the third component as well. And then scalar multiplication, again, it's almost like a distributive property there, where we have to multiply the scalar in all the components. Okay, so let's look at example 3 here. Find the component form and magnitude of the vector having initial point -2, 3, 1, and terminal point 0, -4, 4. And then find the unit vector in the direction of V. Okay, so component form, we have our initial point, we have our terminal point. So in order to write in component form, we just do initial minus terminal, right? So my vector V looks like my initial first component, my terminal first component, which is 0, minus my initial first component, which is -2, so that's +2. Same thing for the second component, so I get -4 minus 3, and then I get 4 minus 1. Simplifying this, I get 2, -7, and 3. So that is my component form of my vector. Now the question says find the magnitude, right? So the magnitude, the formula is the same for the 2 dimension, but now we just have that third component. So remember, I square up the components, add them all up, take the square root. So here I get 2 squared plus -7 squared plus 3 squared underneath the square root. And if I plug out my calculator, I find that that is the square root of 62. So that's the magnitude there. And now finally find a unit vector in the direction. Remember, this is our formula here for the unit vector in the direction. We just take our, we call the unit vector in the direction, we'll call it U for this example, and it's just 1 over the magnitude of V times V. right? So the magnitude here was radical 62. So 1 over radical 62 times the vector 2, negative 7, 3. Scalar multiplication, we just bring that 1 over radical 62 on the inside. So I get 2 over radical 62, negative 7 over radical 62, and 3 over radical 62. So kind of an ugly vector, but that is our unit vector in the direction of v. Okay, so now let's talk about parallel vectors. So we know what it means for two lines to be parallel, right? That means they have the same slope. Here, the idea for two vectors to be parallel is when there's some scalar that makes one equal to the other. So two non-zero vectors v and u are parallel when there is some scalar c such that u equals c times v. So example 3, the vector w has initial point 2, negative 1, 3, and terminal point negative 4, 7, 5. And the question asks which of the following vectors is parallel to w. Well, first we should find what the vector w is, so we'll do that real quick. So remember, how do we find the vector w? It's terminal minus initial, right? So negative 4 minus 2, 7 minus negative 1, so plus 1, and then 5 minus 3. So w is the vector that is negative 6, 8, and 2. And now I need to find if they're parallel, right? We want to find a scalar c such that u is equal to, or actually in this case it doesn't matter if I do a u or a w, so we'll just write maybe w is equal to c times u. All right, I'm going to scooch this up a little bit because that's kind of like separate work there. Okay, so what is w? W is 2, or actually no, what did we find it to be? That's the work we did before, negative 6, 8, and 2, and we want that to be equal to c times the vector u, which is 3, negative 4, negative 1. So we can simplify this even further. Negative 6, 8, and 2 equals 2. Remember, we can distribute our constant in there. So 3c minus 4c and minus c. And we know that these two vectors are equal if and only if their components are equal, right? And so since we have this little equal sign here, we can set each one of these components equal to each other and we'll get a little system of equations. So in other words, I set negative 6 equal to 3c. I set 8 equal to negative 4c. And I set 2 equals to negative c, and see what values that I get for c. So negative 6 equals 3c, 8 equals negative 4c, and 2 equals to negative c. If I get the same value for c for all three of these, then I know that that's my value of c that makes this work, and I know these are parallel. If I get different numbers for c in different in these three equations, then I know that they're not parallel because there's no c that makes all three components work. So let's solve for c. In the first case, we divide by 3. I get c equals negative 2. In the second case, I divide by negative 4, and I get c equals negative 2. And in the third case, I get divide by negative 1, so I get c equals negative 2. Right? So what we find out, we figured out that w is equal to, we found our c is negative 2, so it's equal to negative 2 times u, which means that u and w are parallel because there is some c that makes that work. Parallel only has one r, right? Cool. So now we do the same thing for v here, v and w. So we want to find a scalar c such that, and this time we have w is equal to c times v. W is negative 6, 8, 2. And then we'll just do C and V together. So V is going to be 12, and then we multiply it times C, negative 16C and 4C. Right? So again, we equate our coefficients, or equate our components. So I get negative 6 is equal to 12C. I get 8 is equal to negative 16C. And I get 2 is equal to 4C. So if I solve these three equations for C, I get C is equal to negative 1/2. The second one, I get C is equal to negative 1/2, so we're feeling good. But unfortunately, in the third one, I get C is equal to positive 1/2, right? So these are not all three the same C. So in other words, there's no C that makes this equation true, right? There's no C that can work for all three components. So in other words, there's no C that makes that work. There's no C such that W is equal to C times V, which means that W and V are not parallel. Okay, one last example here just to work more with vectors. So let's write the vector 4i minus 5k in component form. If you look at that, you notice that J is missing, right? So since J is missing, what does that mean? The J component is 0. So when I go to write this, I write this as 4, and then 0 for the J component, and then negative 5 here. Okay, so now the question B, find the terminal point of the vector 7i minus j plus 3k, given that the initial point is negative 2, 3, and 5. Right, so our vector V is equal to 7, negative 1, 3. And we need our terminal point, which we typically call Q, and we'll write that as Q1, Q2, and Q3. So remember how, basically it's like we're given the final answer and we're given the initial point and we have to find the terminal, right? So remember, how does this work typically? Our vector, which is V, is 7, negative 1, 3, and that's always equal to terminal minus initial, right? So terminal first component is Q1 minus the initial first component, which is given by the problem as negative 2. So in other words, minus negative or plus 2. And then our terminal point second component is Q2 minus 3, our initial second component. And then our terminal third component, which is Q3 minus our initial third component, which is 5. So once again, this is, whoops, keep that black, but I end up having the first component equal to this, the second component equal to this, and the third component equal to this. And I can set all those components equal to each other, find Q1, Q2, Q3, and therefore find our point. Right? So I have 7 is equal to Q2 plus 2, negative 1 is equal to Q2 minus 3, and 3 is equal to Q3 minus 5. So here I get Q is equal to 5, Q1 is equal to 5. Q2 is equal to, if I add 3, I get positive 2. And Q3 is equal to, if I add 5, I get 8. So my terminal point is the point Q1, Q2, Q3, so 5, 2, 8. So that is my terminal point here, 5, 2, 8. Okay, part C, find the magnitude of the vector and then find the unit vector in the direction. Right, so again, the magnitude is just square all the components, add them up, take the square root. So here I get negative 6 squared plus 2 squared plus negative 3 squared, all underneath the square root. If I plug that into my calculator, I end up getting the square root of 49, which is 7, right? And in order to find the unit vector in the direction, remember, we call that unit vector u, and it's just 1 over the magnitude of v times the vector v. So 1 over the magnitude is 1/7, and then we're multiplying. Let's practice using the standard notation, this I, J, K notation. So this would be negative 6i plus 2j minus 3k. So I just need to distribute that 1/7, so I end up giving negative 6/7 I plus 2/7 j, minus 3/7 k. And that is my unit vector in the direction of v in the standard vector notation here, the IJK notation. All right, that's all I have for this video. Thank you.